In this video, we solved problem 13.6.012 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use theorem 13.9 to find the directional derivative of the function at the point P in the direction of PQ. And then we're asked to give our answer correct to 2 decimal places. So this is our function, and that's the point P, and that's the point Q. Now remember how we think about this. Now, this is just a cartoon. This is not actually what the function f of x and y equals cosine of x plus y would look like. But f of x and y represents some surface. And it's defined, turns out, for the entire xy plane. We can plug in any xy pair here, and we can compute the cosine of that x plus y. So the domain of this is all of the xy plane. Now, what we want is the directional derivative, or the slope of this surface as we move from the point P, which is x equals 0, y equals pi. So that would just be over here. If x is 0, we're not going forwards or backwards at all. We're just going pi units to the right. And then we want to go from that point to this point. X equals pi over 2, y equals 0. So if that's pi, maybe that's pi over 2. So there's the point P, there's the point Q, and there's the vector PQ. Now, if I wanted to, I could focus just on the XY plane, just that plane down here. And this is what we would have. This is what we would see in the XY plane. The point P is at x equals 0, y equals pi. The point Q is at x equals pi over 2, y equals 0. And we want the slope of this surface. Let's say at the point P, we're going to get some value here. We want to know what the slope of the surface is if we go in that direction, in the direction from P to Q. So you can imagine taking a plane and intersecting that plane with our surface. You might see something that looks like this. It's not exactly the best plane, but I hope you get the idea. So you see where the plane intersects with the surface. Maybe it looks more like that. And we're trying to find the slope of the curve of intersection between that plane and the surface itself. Well, theorem 13.9 says that the directional derivative of f in the direction of u hat is just the partial derivative of f with respect to x times the x component of u hat. So if u hat has components u1 and u2, so it'd be a u1 plus the partial derivative of f with respect to y times the y component of u, or u2. Now we are interested in this at a particular point at x equals 0, y equals pi. So I prefer in that case to use x naught and y naught here. Or we can think of this in terms of the gradient vector. This is the gradient of our function evaluated at x naught, y naught, dotted with that unit vector. Actually, I prefer this version, but I believe this version is what you see in the book in theorem 13.9. And so that's easy enough to compute. You can either do this or do this. They are just the same thing in different forms. So I've got f of x and y equals cosine of x plus y. Now, if I want to use this formula, I need to compute the gradient of f. I need to evaluate it at the point of interest P, which is x naught equals 0, y naught equals pi. So we'll substitute that in, and then we'll find the unit vector that heads in the direction from P to Q. I don't believe this vector is 1 unit long, but we can make it 1 unit long. by finding the magnitude of this vector and then just dividing by that magnitude. So we're just going to resize it so it's exactly 1 unit long. And then that will be our u hat. Then we'll take the dot product of this with that, and that's going to give us the directional derivative, or the slope of the surface in the direction from P to Q at the point P. So first we'll compute the partial derivative of f with respect to x. Now remember, this is not cosine times x plus y, this is cosine of x plus y. So I've got an inside function here. That means I need to use my Calc 1 chain rule in order to compute this derivative. First, we take the derivative of the outside. The derivative of cosine of a function is negative sine of that function. And you want to put the inside function back in and multiply by the derivative of the inside. Since we're taking a partial derivative, we're multiplying by the derivative of the inside with respect to x, treating y as a constant. I'm putting this in brackets over here just to emphasize that this derivative multiplies that entire sine function. But that happens to just be a 1. So we get the partial derivative of f with respect to x equals negative sine of x plus y. And the partial derivative of f with respect to y is very similar. We use the chain rule again because we've got a function of y inside that cosine function. The chain rule says take the derivative of the outside, so of negative sine of that function, put the inside function back inside, and then multiply by the derivative of the inside by the chain rule. Now this is a partial derivative, so we're treating x as a constant and we're differentiating with respect to y. The derivative of this constant is 0. The derivative of y with respect to y is, of course, 1. And so we get negative sine of x plus y for both of these. Now we want our gradient evaluated at x naught, y naught, where x naught, y naught is the coordinates of this point P, because we want to know what the slope of the surface is in that direction from the point P. So our x naught is equal to 0 and our y naught is equal to pi. So our gradient vector is this vector. And we will evaluate this at 0 pi. You want to replace your x with a 0, replace your y with pi, and of course simplify. This just gives us the sine of pi times -1, sine of pi is 0. So the gradient at that point is actually really boring. It's just the 0 vector. If you're saying, okay, well, what does that mean? That means the slope in the x direction and the slope in the y direction are 0 at the same time. And we'll see later that that means that that point P must correspond, well, probably corresponds to a minimum value of the function or a maximum value of the function. But we'll discuss that a bit later. Okay, so we want to take this vector, which is the 0 vector, and we want to dot it with u hat. I think everyone can tell that no matter what u hat is, we're going to get 0. So we'll have 0 times u1 plus 0 times u2, which is of course 0. So the answer for this problem is 0. Now, just in case you are working a different problem where your gradient at the point of interest is not the 0 vector, I want to show you how to compute the components of a u hat. Okay, so this is the process that we would follow for any type of directional derivative problem. I'm looking at this formula and it's reminding me what I need to do. I need to compute the gradient vector and I need to evaluate it at the point of interest. So this first part was us computing the gradient, which meant computing the partial derivative of f with respect to x and the partial derivative of f with respect to y, and then putting those two pieces together into, or to make that, those two pieces, the components of our gradient vector. And then we evaluate that at the point. and it turned out to be the 0 vector. If it wasn't 0, from here, I would find the unit vector in the direction given. So we were told to start at P and go to Q. So I need the unit vector in the direction of PQ. So first we would find the vector PQ. To do that, we just take the coordinates of Q, which were x equals pi over 2, y equals 0. And we subtract the coordinates of P, which were x equals 0 and y equals pi. So we've got pi over 2 as our x component of the vector PQ and negative pi as the y component of our vector PQ. Then we find the magnitude of PQ. Now, one way that you can find the magnitude to make this calculation a little simpler is to just factor out that pi. So you'll have that there. So I want the magnitude of pi times this vector. Well, the magnitude of pi is just pi, and the magnitude of that vector can be found this way. Take the components, square them and add them, and take the square root. So we'll have pi times the square root of 1/4 plus 1. 1 you can write as 1 over 1. We want to get a common denominator, so we'll multiply by 4 over 4. So we'll have pi times the square root of 5 over 4. We end up with the square root of 5 times pi, and the square root of 4 can be simplified as a 2. Okay, so this is my magnitude. That is my vector PQ. And we want the unit vector in the direction of PQ. So you just take the original vector and you divide by its length. Now, dividing by this fraction is the same as multiplying by the reciprocal. So I'll take that and flip it and multiply it by this vector. And the vector had components. Pi over 2 and negative pi. Actually, the 2's will reduce here and the pi's will reduce on that x component as well. And we'll just be left with 1 over square root of 5. And over here, the pi's will reduce and we'll just have negative 2 over square root of 5. That's our unit vector. Once you have the unit vector and that gradient evaluated at the point, you would just take the dot product. So we would have 0, 0 dotted with this vector with components 1 over square root of 5, negative 2 over square root of 5. And so we just have 0 times 1 over square root of 5 plus 0 times negative 2 over square root of 5. And then you do the arithmetic. In this case, we get 0 because the gradient was pretty boring. Didn't have, actually it depends on how you look at it. It made this calculation pretty simple, but actually having a gradient vector of 0 is pretty insightful, saying the slope in the x direction and the y direction are both 0 at the same time. So maybe we're at a minimum or maximum value of z on that surface. Of course, this is a cartoon and it's not actually the graph of cosine of x plus y. I hope that helps. Let me know if you have any questions about this problem or similar problems.